Yeah. Right. Okay. So welcome everyone. So I'm Niladri Banerjee from Loughborough University. So welcome to this online tutorial series on quantum matter meets topology, organized by the Society for Promotion of Academic and Research Collaboration from the Government of India. And so this is through a bilateral grant between India and UK that Professor Ratnamala Chatterjee at IIT Delhi and I at Loughborough University, we jointly hold. So we are organizing the series of talks as a part of this grant. And as you might have seen already from the posters, that there will be 3 speakers. So today is Professor Saroj Dash, and on Monday he is going to continue the talk. And on 3rd and 5th of March would be Professor Sumanta Tiwari from Clemson University in US. If you note that the times are different from on 3rd and 5th of March, it's from 10:30 a.m. to 12:30 in the afternoon Indian Standard Time. However, today it is 3:30 to 5:30 p.m. IST, which is 10 to 12 GMT. And on 24th and 25th of March, we have the last speaker of the series, Professor Siddharth Parameswaran from Oxford University. And it's again going to be at the same time, 10 to 12 in the morning GMT and 3:30 to 5:30 in the afternoon in IST. So, right. A bit of housekeeping rules for this talk is that we are going to, okay, I already see a hand up, so I'm going to take that later. So we are going to accept questions for this talk every 20 minutes, as Professor Dash has already agreed. And the idea would be that you put your questions in the chat, and if that involves some formula or it's a bit extensive, you can raise your hand and we will try to unmute you. But please do keep in mind that we have quite a number of attendees for this session, and it may not be possible to take all the questions in that break. So that's why after 50 minutes of the talk, we are going to have a 10 to 15 minute question answer session, and we will try to take all the questions. So it's a good idea if you could put all your questions in the chat, so that we can, even if we miss the question in the first session, we can take it hopefully during the 10 to 15 minute break. And we are going to wrap up everything in 2 hours. So type your questions, and if it's not at all possible to type the question, raise your hand, we'll try to take that. And as I mentioned, the talk is being recorded. So, right. So now I'm going to introduce the speakers. So today's speaker is Professor Saroj Dash from Chalmers University of Technology, and he is an associate professor at the Department of Microtechnology and Nanoscience, and he leads the Quantum Device Physics Lab. So Professor Dash received his PhD in physics from Max Planck Institute in Stuttgart in 2007, and he followed it up with his postdoctoral years were spent at universities of Twente and Groningen in the Netherlands. After his postdoc, he joined Chalmers University of Technology in November 2010, where he's now leading this group in quantum device physics. So his research interests are on electronic charge and spin transport in graphene, semiconductor nanostructures, and two-dimensional materials in general, and topological insulators. So he has kindly agreed to give a talk today on spin-polarized electronic transport in semiconductors, graphene, and topological matters. So what I'll do now is I'll request all the other participants to also turn off their camera except Professor Dash, and I'll put the spotlight on him. Hopefully that works out fine. Okay, Ali, could you put the spotlight? I can't see it here.
Yeah, I believe you're now spotlighted. Yep. So.
Yeah, I hope you can see the screen now.
Yes, we can. Yeah.
Okay. Okay, so thank you, Niladri, for kind introduction, and thank you and Professor Ratnamala Chatterjee for this opportunity to present some of the things we are doing, and I'll try to keep a overview of the field. And so what I'll tell you today about is spin polarized electron transport. So in different materials, including metals, semiconductors, and topological materials. So, so as you know, so how things are happening in nanoelectronics. So you must be, uh, you must know from these pictures that it's a metal oxide field effect transistor semiconductor with semiconductor substrates, and they are scaling down with time. And now we are in a regime where the channel length is 10 nanometer, and there is a problem already in the material point of view, and people are looking for new technology to take over this. Also, in the same time, what we are looking is how the magnetic data storage is moving. So from hard disk to magnetic RAM, and people are trying to combine these magnetic RAMs with semiconductor channels so that our memory and processor can be on the same chip. So it will help to integrate both logic and storage in single device. But slowly, what can happen in future because of the requirement of faster and smaller transistors, and also the very highly efficient artificial intelligence and Internet of Things. So maybe the spin property of electron will have lots of importance because for most of the applications, so it will be very specialized and you need non-volatile uh, memory applications. So in that case, so what can happen is that you will see more spintronic devices. So for example, presently, so such developments with spin polarized charge current, and then you can move to electric control of spins, and then you can go to pure spin currents. And also in the parallel, the quantum computing with spin states are also developing. So that can be very challenging and it needs lots of research from the material perspectives. So what kind of material is important for these applications? So I'll divide my talk in these 2 days into these 4 parts. So today I'll first start with metal spintronics because everything started from there. And then I'll also cover the semiconductor spintronics part. So this will be today. And in the next lecture on 22nd February on Monday next week, so we'll talk about graphene and other 2D materials, heterostructures, and also topological materials. So that is the plan. So today we'll go about metal spintronics. So if we really look where we want to contribute in with the spintronics, so the present state is like this. So the non-volatile part is the data storage with ferromagnets. So this is the hard disks you have, and the read heads used for data readouts. So these are based on metal spintronics. But the other memory and logic functions, they are more based on semiconductors, so which is volatile. But the target is maybe after 10, 20 years, what you can see, more spin related things are catching over to this hierarchy. So maybe in future you will be able to do more logic functions with spins and all the random access memory functions with also spins. So maybe most of you know, just to keep it simple, I start with introducing, so what is the spin degree of freedom? So spin is the quantum mechanical property of electron, as you know, and it can have spin up or down, you can say, because of the right and left uh, revolving electrons. And so you can use that for the logical operations, for example, 0 and 1. And also you can use it, spin is a quantum number. You can use also for quantum computers where you will have more options. So what is the advantage of using spin? Because it can consume less energy, because if you want to manipulate the charge, you spend in electron volts of energy. But if you interact with spins, you can manipulate the spins with milli electron volt energy. So that is the advantage. And over that, you will have non-volatile memory, and you can integrate the logic and storage in a single device. So let's start with the metal spintronics. So most of you know magnets. So magnets are in our everyday life. So everywhere you see magnets. So for example, starting from headphones to magnetic levitation trains and any turbines, medical applications. So magnets are everywhere. Also, now your roads will be magnetic because of the autonomous driving. So Volvo Cars is already testing the tracks with um, magnetic elements so that you can sense and track your car automatically there. So that will be the future roads, how it look like. Then you need lots of spintronic devices to detect those things. And also for medical applications, as you know, magnetic nanoparticles are very much interesting. So this is a broad overview, but when coming back to the data storage, so how the data storage looked like maybe 40, 50 years ago, that so you see this is the magnetic data storage devices here, and they were mostly using the magnetic coils. And then the magnetic tapes, floppy disks, compact disks, so they are developed. Then you have the hard disks. And now you are storing lots of data in cloud services, for example, Google, Microsoft, things like this. And now the data centers looks like this. So it's very similar to what was before, 30, 40 years before. So both have big rooms with lots of things, but the major difference is that the amount of data you store have increased millions of times. So you can, with the same space, you can means save lots of data. And why we need that? Because we have so it's an information technology society now. Everyone using mobile phones, laptops, and we are generating lots of data so that you also click lots of pictures. So where to store them? So that is the main challenge. So with that, so I'll again go back to several tens of years ago. Then in 1970s, what people actually used for magnetic data storage. And already from that time, spintronics was there. For example, so spin orbit scattering actually helps to make a anisotropic magnetoresistance device. So if you have only a ferromagnet, for example, so this is a ferromagnet, and if you apply current, and so the current have different resistance depending on the orientation of the magnetization. So this is the resistance change with angle, what you see. And such principles like anisotropic magnetoresistance, of course, it was discovered long ago. So these were used for magnetic recording. But they are a bit less sensitive because the change in the magnetoresistance was around 1%. And so they are also a bit larger devices. So how to improve? So when you go for new data storage, what you should look for is the more sensitive electronic devices or spintronic devices. So you have to look for spin polarized electrons. So you know from where you can get spin polarized electrons. So they are mostly ferromagnets. So ferromagnets, for example, iron, cobalt, nickel. So they are magnets at room temperature. So if you look at the density of states, how this look like is at the Fermi level, you have upspin electrons more than downspin. So density of states is different. So that means also the conductivity for the up and down spin electrons will be different. And that depends on the diffusion constant of electrons. So this up and down electrons, they will be different. And this comes directly from the um, Mott formula that Mott proposed that there will be two channels, two parallel channels in a ferromagnet, one for upspin, other for downspin. and they have different resistances in this material. And after several years, people found out that, yeah, that is true. And these ferromagnetic materials, when the current comes out of them, uh, they are spin polarized. So in 1998, this paper shows that what is the spin polarization of this iron, cobalt, nickel, and their alloys, and any other ferromagnet. So it's around, let's say, 40 to 50%. And you can find other materials with 100% spin polarization, but they are mostly at um, low temperature. And these measurements were done with superconducting point contacts. So superconductor in the gapped states, it's 100% polarized. So if you put a point contact with another ferromagnet, you can find the spin polarization. So these things helped Peter Gunberg and Albert Fert to discover this giant magnetoresistance. So what is the giant magnetoresistance? I'll come back there after this slide. So just introducing different spintronic effects were introduced during these years. For example, giant magnetoresistance, tunnel magnetoresistance. This is the spin transfer torque or spin transfer uh, oscillators one can do. This is the spin orbit torque. So spin orbit coupling in the material can also switch the magnets. So these are quite useful for developing the spintronic devices, for example, in hard disk or magnetic random access memory. So what is giant magnetoresistance? So maybe most of you know already this. Let me just put it in simple words that when you have two ferromagnets separated by a thin layer of metal, so depending upon the orientation of these two magnets, so either electrons can pass through or they can reflect when they are antiparallel. So when they are parallel, electrons can pass through. These structures, resistance is low, and when they are antiparallel, so resistance will be higher because electron have to reflect back. So they saw this resistance change when they apply a magnetic field to make it parallel and antiparallel. And these are actually iron chromium multi-layers. So to increase the sensitivity of the devices. And the change in the resistance what they saw was around 70%, which was very large compared to anisotropic magnetoresistance, which was around 1%. So this gives rise to a name called giant magnetoresistance. And this has been used in magnetic hard disks. So then after several years, people actually used tunnel magnetoresistance. So in between these two ferromagnets, they put a magnetic, this is an insulator, magnesium oxide. It's a normal insulator. So electrons have to tunnel through. And it depending on the availability of the density of states and also availability of electrons in the other side. So they can either tunnel through or not. And the spin polarized tunneling is the important plays an important role here because once you have a, let's say you have lots of electrons which are polarized here, but if you don't have an available state on the other side, so you cannot tunnel through. So that gives a change in the resistance when they are parallel or anti-parallel, huge, like up to 1000% at low temperature and 400% at room temperature. So this is the standard material now used, this like magnetic tunnel junctions in many magnetic hard disks for the read-write heads and also for magnetic random access memories. So this is how it looks like. It's a bit more complicated than what we see. So this is your magnetic hard disk where you store the data. And this is the read head. And this read head, if you magnify here, you see number of layers. So these are different ferromagnetic layers and tunnel barriers here. And they will be able to read or write in your magnetic bits in this thin film of ferromagnetic material because they are perpendicular materials. So you have your this read heads should be very sensitive and very small. That is only possible with this tunnel magnetoresistance devices. So next thing was how to utilize again for the memory applications. For example, not the just storing information, in the magnetic disk and reading by magnetic tunnel magnetoresistance devices. But if we can make a memory device out of only this spintronic principle, so then in 96 there was proposal about spin transfer torque. So what is spin transfer torque? Because this is quite interesting that when you have a ferromagnet with some polarization or magnetization, which is a bit different from the here analyzer magnetization, which is a ferromagnet 2, and you have a special layer. It can be tunnel barrier or a metallic layer. So when you pass a current, so it will be spin polarized, and the spin polarized electrons can enter the second ferromagnet and exert a torque on this. When they exert a torque, then you will feel like a damping like torque or spin orbit torque like things. So the magnetization will oscillate. So you can get a oscillating frequency in the gigahertz. So this is like a nano oscillator you can make out of it. But if you apply a current which is a bit more than the threshold current, which is then you can switch the magnet. The magnetization can switch. So there's such a switching has been observed also like that. So you apply a current, then at some point you switch the second magnet and you see a change in the resistance. And such switching has been used in here in the magnetic random access memory devices. And this is a CMOS device, as you see, source drain with semiconductors. And on top of that, they integrate this magnetic tunnel junction, which is a switch actually to do the memory functions. And so this have lots of application for communication. For example, these oscillators can be used in your mobile phones, and the memory devices you already have for several applications, for example, the space applications. And maybe yesterday you saw how the robot landed on Mars. So this should have some spintronic devices because they are more resistant to radiation hazards. Semiconductor memory can degrade with radiation. Okay, so that was the part where we can induce spin polarization, and we can also use the spin polarization to change the magnetization magnetization dynamics of another magnet. So that can be used for different applications. So if you have any questions, we can also take it.
Yes, okay. I think it should be a good point to take questions. Ali, could you confirm if the chat is enabled? I think there were some problems.
I'll just type in something, see if it works.
Yeah, it does.
Yep, okay.
Okay, so if anybody has any questions, okay, I see somebody raised hand. If you have any questions, if you could type it in, be useful.
Or we can move on, then we can have.
Yeah, I think we can move on and then take it later.
Mm-hmm.
Okay, so this whatever I showed you now, this giant magnetoresistance, tunnel magnetoresistance, and the spin transfer torque, this is all already in the industry level now. So you can buy these products in market for this magnetic random access memory or the sensors of GMR, TMR. Then the next thing was how to increase the efficiency of this spin orbit torque, spin transfer torque. That was the discovery, which was actually, it was proposed in 71 even, 1971. Then it was rephrased in 1999. It's called spin Hall effect. So what is spin Hall effect? So you know what is normal Hall effect. So if you take a semiconductor or a metal, so you apply a magnetic field perpendicular to this, and when you apply a charge current, so electrons will go to one end of the material here, and the holes will be at the other end. So that will create a voltage and you can measure with magnetic field that is called Hall voltage, and that helps in many understanding the material properties. And this is the most usually sensors, magnetic sensors, because they are very cheap and you can sense very sensitively the magnetic fields. So you will find applications of this Hall sensors in all your home appliances and cars and everywhere. But also you know that in magnetic materials, when there is a magnetization in the material, so that also gives a Hall effect, but it's anomalous Hall effect because it behaves differently and it shows a magnetic hysteresis behavior. Hmm? So that is the advantage of anomalous Hall effect is you can use that in your metallic ferromagnets to study the behavior of the magnet. Okay, and just in 2005, 2004, the spin Hall effect was first realized in semiconductors. And when you have a material, you don't need to apply magnetic field or you don't need magnetization in your material. But when the material have huge spin orbit coupling, for example, platinum, gold, and semiconductors like gallium arsenide. So you just pass a current here. You don't apply any magnetic field or any there is no internal magnetization in the material, but the electron spins. One spin will be accumulated in left, for example, and the down spin will be accumulated in the right, and that is the spin orbit scattering. And this, how to understand this? There was many uh, papers already before that to explain such behavior. For example, there can be some scattering from the atoms here. So if these atoms are very heavy, like platinum, gold, and such heavy tantalum, so what can happen is that the electron can scatter. This is called skew scattering if it happens in the one side, and it's called side jumps if it happens on both sides. So there are just scattering mechanisms, and there is also a intrinsic effect, intrinsic spin Hall effect, which comes from the band structure of the material. So let's say you have a Raspberry type of band structure. So the band is splitted due to spin orbit coupling. And when you pass an electric field, when you apply electric field here, so you get a spin polarization. Yeah? So this can be due to spin orbit interaction in your material. So this is again a schematic. When you pass a charge current, your spins are accumulated on both sides of the material. And this gives a spin current in this direction. And that is called pure spin current because there is no charge current here. Okay. Then people thought, so it's exactly after, so as you see, spin Hall effect was discovered in 2005, as I showed here, or 4. And exactly after 5-6 years, so what people could do is they could utilize to switch a magnet. So for example, here, either you take a metal of tantalum, platinum, or tungsten, which is very heavy. Then you put a magnetic element here, nanomagnet, with some magnetization orientation. It can be in plane, out of plane. So you have to deal with other basic things here to switch those magnets. But when you apply a current here, so you create spin with the red spin going down to the other surface, the green spin going up to the top surface, and this green spin can switch this magnet. Okay, and how to read out that? So you can put a tunnel barrier and put another magnet. When this lower magnet close to this metal switch, then you can see a change in the resistance depending on the magnetic orientation between both of them. And so what you will see is switching in your resistance. And that's what exactly people have seen in this 2012 paper and 11 paper here, that when you apply a current in your metal, you will see the change in the resistance of your device because you switch one of the magnet. And so this is called spin orbit torque. So the spin orbit in this material and the spin polarization here exert a torque on your magnet, and this gives a switching. And this torque can be different kinds. So from different types of experiments, people can find out which torque is dominant in which material and which interface, because this is very sensitive to interface here. And there are torques like damping like torque and field like torque. So the damping like torque comes from the spin orbit effects mostly, and that is more useful for switching of the magnet. Okay, so that was the basic spin Hall effect. But recently, so going forward, I can show you that in 2019, people discovered magnetic spin Hall effect. So magnetic spin Hall effect means what? So it should be dependent on magnetic field in your material. Okay, and that was discovered in a non-collinear antiferromagnet magnesium. So magnesium is a new material. It's a antiferromagnet. Antiferromagnet means the spin should cancel out, but it's a non-collinear antiferromagnet. That means uh, in this material, so the magnetization is not linear, means it's collinear, not collinear. So that means when you measure in such material a anomalous Hall effect, you get a net magnetization. Hmm? It's an antiferromagnet, but you can find the magnetization. So what people have done is that they wanted to see if this material can give a spin Hall effect and if it is dependent on the magnetization of the material. Because this is also theory paper just came out last year. So they show that what can happen is the spin Hall effect. So when you apply a magnetic field or electric field in the material, so spin Hall effect, uh, these blue lines, so the spins are accumulated on the surface with these blue lines. So when you change the magnetization, the electric field is the same from in plane to perpendicular, or from inside the material to other side of the material. So you change the magnetization orientation. So what should change? The spin Hall effect direction should not change, the conventional spin Hall effect. But if it is magnetic, that should change, because the magnetic, what you see here when magnetic field is pointing into the screen here. So you see the spins coming out from magnetic spin Hall effect is pointing outwards. But when you change the direction of the magnetic field, spins are pointing inwards. So this effect was not known before, but it has been discovered now. So they could see that when you switch the magnetization with the magnetic field from this direction to the other direction, you see a change in the resistance, which is also reverses the sign. So that gives rise to this called magnetic spin Hall effect. And many people, as I know, are working on antiferromagnets. And if you find a non-collinear antiferromagnet, so this should show such behavior. Another thing, so it's a topological workshop. So it will be interesting to show how topology behaves in the magnetic systems. So as you know, so you have spin orbit. Let's say you have a magnetism in your system, you have a magnetic material. But some magnetic materials have, let's say, low spin orbit coupling. But if you bring your magnetic material in close proximity with this high spin orbit material, for example, here, let's say you have a platinum, and here is a ferromagnet, for example, any cobalt, nickel, or iron. So what can happen at the interface? So at the interface, your spins will experience more spin orbit coupling. So in the ferromagnet and antiferromagnet, you know how the interaction takes place between, this is the two spins, and they are interacting with the exchange constant here. But in the when you have a spin orbit coupling added to this magnetism, so you will have a exchange interaction, which is called DMI. So Jablonski-Moria interaction. So this interaction can produce some spins in a canted structure. So, and you will find such magnetic structures. For example, it's called skyrmions. And they can be very small. It can be from few nanometers to even uh, hundreds of nanometers, but that can be controlled with different materials and interfaces or spin orbit and magnetism. So people have also find out that in such a system, for example, here a um, uh, 2D is a magnetic material like oxide with platinum, and they see when they measure the Hall effect with the magnetic field. So they see these peaks at these different fields here, and they are hysteretic. And these peaks are contributed to the skyrmions. And when electron pass through such a skyrmionic structure, so they will be deflected. And this gives rise to this anomalous behavior again in the anomalous Hall effect. And this is due to called topological Hall effect. So this is another addition to the Hall effect. So if you follow what has been done with the Hall effects, so Hall effect was there with a normal metal magnetic field. Then you have anomalous Hall effect when you apply a magnetic material in the system. Then you saw spin Hall effect comes from the spin orbit coupling, and the topological Hall effect comes when you have both magnetism and spin orbit coupling. It gives rise to these new magnetic structures called skyrmions, and they are actually topologically protected, so you cannot destroy them simply. So this gives rise to this topological Hall effect. So these are very new developments in the field of spintronics. And people are trying to also control the magnetic skyrmions. So you can create these skyrmions and you can control them by spin orbit torque. For example, here, so people have tried to, this is a review article, you can see that you create these skyrmions, and by using a high spin orbit material, so when you pass a current, you actually create the spins again, and these spins will be able to change the magnetic configurations of these skyrmions. So you can create and control the skyrmion property by all electrical means. Okay, so these are the basic magnetic properties. So how then we can use spins for logic applications? So it will be beyond the memory devices. Okay, so there have been many proposals. For example, in 2010, there was a proposal for all spin logic. And in 2019, there was this major spin logic, which is a majority gate. And this all spin logic is based on the idea that you should have a channel material where electron spin polarization can flow. And then you should have a nanomagnets so that you can communicate this information from one magnet to other by the spin current. And this spin current, let's say you switch the magnet by some means, then you should be able to do the logic operations. And in the major logic, so it's called magneto-electric spin orbit logic. So you use spin orbit effects to switch magnets, and then you can have different channel materials for different inputs, and then you can get the output that you can control by this gate. So that was the basic principle of this logic functions. So to do that, what we need to know, so far what I have showed you that we can transport spins in these metals or the structures like TMR, GMR, few nanometers. So it's not long distance transport. But for these devices, you need to maybe think about transporting spins few microns at least. So that will be advantage. Then we need to understand how spin transport occurs in a normal metal, for example. But if you want to consider normal metal for spin transport, you have to consider a low spin orbit material. For example, aluminum. So here I am showing how we can inject spins from the ferromagnet, and spin accumulation takes place in the normal metal, for example, aluminum here. So these are the basic things. So the ferromagnet is a simplified band structure here. So you have spin density of states and you have more spin down, for example, at Fermi level. And this is the density of states for the aluminum. And this is the s electrons here. And you have equal number of up and down spins. But when you apply electric bias, so or you apply electric current here, so you inject spins from the ferromagnet into the normal metal, and this will be non-equilibrium spin. And what you will do is you create a spin splitting in the band of aluminum close to the interface. So we'll see how long the spins can go in aluminum. But close to the interface, you create a spin splitting. So between up and down spins. So the mu up is the up spins, mu down is the electrochemical potential. It's for the down spins. So once you do that, you can also detect those spins. So there is a question, but I'll come back. So I'll finish these slides in a few minutes. We'll discuss that after this. So spin injection and transport in aluminum. So what people have done is that you have aluminum electrode here, then you have ferromagnets. So you apply a current here, and so that you inject spins at this point. So spin will go both directions. This is the cross-sectional view. So spins are going in both directions. So you have a tunnel barrier to decouple ferromagnet from the aluminum, so that you don't have any proximity effects or any kind of conductivity mismatching here, because spin again can go back to cobalt. So once you inject spin, you create a chemical potential difference between up and down spin at the interface in aluminum. Then, because it's a non-local measurement, so current is going here and spins are diffusing in this channel. So you have this splitting of the electrochemical potential. So they will decay with distance because it's not a magnetic material, it's a non-magnetic material. The non-equilibrium spin you created will decay in this material. And then at some point within the spin diffusion length, you put a detector ferromagnet, which is a second cobalt here, as you see here in the picture. So that can detect the spin you created in aluminum. So how to detect that? Because you can switch the magnetization of these two ferromagnets independently. They have different widths, so the different coercive fields. So you can apply a field, which is a different field to switch them independently. So here you see the measurements at room temperature or also at low temperature. So the switching field is different because this is the magnetic field, in plane magnetic field, which changes the magnetization of this cobalt 1 and cobalt 2. So when both switches, you get to this parallel state here. And when one of them is anti-parallel, you go to this state. So you see the change in the resistance or the voltage when you try to detect the spins. This is called spin valve measurements. So how to find the spin relaxation time in this material? So you can make devices with different channel lengths. So from here 500 nanometer to 1.4 micrometer. So this is all length in nanometer. So you can see the magnitude of the signal changes exponentially. And this is the resistance. What you see is that it depends exponentially on the length of the channel. And also it depends on the spin diffusion length. So by fitting this equation by these data points, you can find spin diffusion length in aluminum, so which is around 600 nanometer. Okay. So once you do your spins are injected into graphene, so you can detect by changing the magnetization and doing the spin valve measurements, but you can detect also by another method. It's called spin precession method. It's called Hanle spin precession, and because it was discovered by Hanle in 1930s, when you apply a magnetic field, the polarization of the atoms go down with applying higher magnetic field, which is perpendicular magnetic field here. So you have a ferromagnet, is a non-magnetic channel, spins are going here, and you apply perpendicular magnetic field. So what will happen? Spins will precess when they are going in this channel, and you will be able to detect at this electrode. So you can do both for parallel and anti-parallel. So parallel, it will see like this such behavior. And for anti-parallel, you see this dotted lines. So the spin signal should behave like this with angle. But what happens that you have also flip scattering in your material. So this you have a spin lifetime in your material. So if you consider that, so your spin signal will decay much faster. So what you will see a signal when you apply a magnetic field, but it depends also on the channel length because spins are precessing while they are moving. So if you detect here, for example, so spins are not completely out of plane. But if you detect here, they are 90°. But if you detect here, it's out of plane. Okay, so what you will see that with different length of the channel, 0.5 to 2 micrometer, 5 micrometer. So you should see the Hanle line with the magnetic, this voltage signal with magnetic field that will have different line widths. So when you have such a signal for the longer channels, that means spins are precessing completely. And so all the spins are in the out of phase here. So people have done such measurements to find out spin lifetime in the different channels. And this is a equation, simplified equation you can use to find out this how spin signal voltage depends on the diffusion constant here because you have spin have to diffuse in the material. So this is the precision term, this is the Larmor frequency term, and dephasing it's a lifetime, spin lifetime. Then the question was, let's say you can transport spin in non-magnetic material, but how you can use it. So in 2008 already people have shown that. So if you have a nanomagnet, so for example, this picture, you have some permalloy nanopillars. So you can send a spin current in this copper wire and switch one of this magnet just by applying a current without magnetic field. So this is the zero magnetic field here, but at low temperature. So you apply this DC current. So it should be a pulse current, not to heat up the samples. And so you can switch the magnet and you can see this hysteresis behavior. So this is how a pure spin current induced in this copper channel can switch the magnetization of a electrode. So that can be used for the spin logic applications. So with this, I would like to summarize this metal spintronic part and first half of today, that what we have seen that how this GMR, TMR, and spin transfer torque are used in industry now. And in few years, you will see spin orbit torque will come to industry because they have already shown very fast switching properties and very small scale devices now. And in future, maybe you will see more skirmions, how to play with these things. So this is very hot research topic. And maybe some spin logic applications will appear. So with this, I stop this first part of the talk and we can discuss some of the questions.
Yeah, thank you, Saroj. There are 3 questions, I believe, already. So in the chat, can you see the questions?
Yes. So first part of the question, I have few questions. Can we kill magnetic order, let's say by applying pressure, and preserve topology? Can we turn non-collinear antiferromagnet axion TI into a topological insulator times? Okay, so first question. So there are 2 questions here already from Vikrant.
There's a third question which is just above, but from Manipal Singh. But
yeah, I'll come back to that.
yeah, we can take it. Yeah.
So can we kill magnetic order by applying pressure and preserve topology? So I don't know whether you can kill the magnetic order, but you can tune the magnetic properties and the interactions for sure. So these are I have not seen. So I don't know actually, because if it is 3D materials, how sensitive they are to pressure. For example, maybe you need very high pressure in gigapascals to do that, but it may not kill magnetic order. But in the correlated material systems, for example, like this oxide interfaces and this twisted bilayer graphene systems, so they are more sensitive because they are correlated phenomena and magnetism coming from the correlated electrons. So that may be more sensitive to this pressure and other parameters. Maybe somebody here can answer that better. Okay, the second question is, can we turn a non-collinear antiferromagnet Ti into a non antiferromagnet axion Ti into a Ti? Okay, so as I know, the reverse case is possible. You can, for example, make a topological insulator by applying a magnetic field. So you can change the band structure with a high magnetic field so that you can go to some wild semi-metal phase. So normal topological insulator to wild semi-metal phase. I actually don't know whether this case, what you propose here, is possible or not. So do we allow Vikrant to comment or something? Or we just go to next questions?
I think yes, he says thank you. So hopefully his question is answered.
Okay.
I think we can move on to the next question.
Yeah, the first question was from Manipal Singh. Question is there any particular symmetry which is protecting these Fermion phases from external perturbation? Yeah, so this is like a topological phase of the material. So this is, for example, topological insulators. So you have to actually put some magnetic impurities or something to destroy them. So similarly, these skyrmions actually appear because you create a phase where due to spin orbit coupling and magnetism. Of course, you can destroy them by temperature or hammering them if you destroy one of the magnetism or spin orbit. But they are topologically protected, and that is the one of the topological states of matter. So it's like electrons behave like some quasi particles in this phase. Then another question from Manipal Singh: is the momentum relaxation time related to the spin relaxation time? Can we get this spin diffusion length longer if we make our conductor more ballistic? Okay, so yeah, so you have to consider two separate quantities for momentum relaxation and spin relaxation. Of course, they are related, but momentum relaxation time can be in femtoseconds or picoseconds. But spin relaxation time can be nanoseconds and microseconds. So, for example, spins can scatter many times in, for example, aluminum or graphene with low spin orbit material, but spin orientation can still survive. For example, high spin orbit material, so the momentum and spin scattering are very much related. For example, in platinum, once spin electron scatter means spin is also scattered. Also same as with a topological insulator. So they are very highly coupled. So it's like spin momentum locking. In that case, so spin relaxation and momentum relaxation, they are same. But in case of graphene and aluminum, so graphene case I'll show you next week. So spin relaxation is much, spin relaxation time is much higher in nanoseconds for graphene and aluminum. Do I miss any questions?
I don't see any other questions right now. I have one quick question.
Yes, please.
Is that if you could comment on the sort of material aspect, especially the interface with these is antiferromagnets. I mean, are there any special consideration of interface or growth related, which is different from the conventional, like the spintronic stuff that we do? I mean, do they need to be epitaxial always, or can they be polycrystalline? Yes.
Yeah, so this was actually done in a single crystal. So it's a single crystal of magnetine. Then they actually caught it with by FIV to make the device, focused ion beam to make a small device. But I saw some recent papers from them, and they grow by sputter deposition, the similar material. And sputter deposition, as you know, it gives polycrystalline quality. And they still see very good non-collinear magnetic behavior, and also anomalous Hall effect up to very high temperature, up to room temperature and more. So still you can have antiferromagnets with lots of polycrystalline materials.
Okay. And I was wondering that if it is in this antiferromagnets, if it is possible to also couple them with optical pulses, for example, to switch the spins, is there this option of this degree of freedom?
Optical, I think people have done with microwave range,
okay.
in the microwave range.
Yeah. Okay.
So people are using, I think, for the spin pumping. So you create spin dynamics, and so as you know, so this antiferromagnets, they can work at high frequency. So they're better for spin dynamics, and they have, because they have a faster spin dynamics. So
Yeah.
for high frequency spintronic devices, people are preferring to go for this antiferromagnets. So I am not a very expert in this because I didn't work with antiferromagnets,
Yeah.
but it's just an interesting topic at this stage.
Yeah. We have one more question from Vikram.
Let me read the question. Do we have a well-defined set of symmetries that can completely define a particular class of topology? Let's take the example of non-magnetic 3D TI. So yeah, so I'll come back to this more topological stuff in next week class. So maybe that time we can discuss more if it's okay.
Yeah, I think, once you introduce it a bit more, it will be relevant to discuss it then.
Yeah, I keep this question in mind.
Yeah. Okay. So I don't see any other questions. Maybe we can start and then come back. 20-25
So do we
minutes.
have a break or something?
Yeah, and
how long?
We're planning to take a question answer break. So I think we can just take a sort of a 10 minute break.
Okay, then, yeah.
And if anybody has any questions in the meantime, please feel free to put it in the chat section, and then we will restart in 10 minutes.
Okay,
That's all right. Yeah. Shall we restart?
Yes. Yeah.
10 minutes. We didn't get any additional questions, so we can directly start and then maybe in
Okay.
25 minutes or half an hour take questions.
Okay, good. So I think you can hear me now.
Yes.
Yeah. Okay, so let's go to the second part of this tutorial. It's semiconductors electronics. And you know why semiconductor is interesting. So what we try to do with the semiconductors is that do lots of logic operations and also some memory devices with mostly in the processors you see silicon, and then how to combine this magnetic information into the semiconductors. So can we develop spin-based transistors, switches, or logic circuits? So that is the main question we'll be trying to discuss today. So you know there are many advantages in the semiconductors. For example, we can engineer the band gap, carrier density by applying electric gate, and spin lifetime can be much longer than in many metals. And technology base is also mostly semiconductor base. And in the ferromagnets, you have non-volatility. So then you have some switching, fast switching, and high Curie temperature you can get. And also you can combine spin transport. And there is a technology base called magnetic recording and magnetic RAM. So can we combine both into the same device? So if we go back, let's say 20 years from now, so we have seen that people have used this magnetic impurities up to 5%, for example, manganese atoms in the gallium arsenide. So these are substitutional atoms here, the manganese. So manganese have magnetic moments, and these magnetic moments are understood to be interacting by the carriers like electrons or holes in this gallium arsenide. So it's a carrier mediated magnetism in this gallium manganese arsenide, and the Curie temperature is around 150 or 200. So people are still sometimes working on this. And so these properties can be very well controlled because you can control the carrier density, and because it's a semiconductor, and you can do this all by electric means. So for example, here's the you have these magnetic moments and the electrons or holes that mediate the magnetism between this. So the advantage of semiconductor, as we discussed, so you can apply electric field at the gate voltage to tune the carrier density. So this is one example from a paper in 2000. And so this is a indium manganese arsenide system. So they are grown on different semiconductors layers. So this is the magnetic layer, as you see here. Then you have an insulator and you have a gate, metal gate. When you apply a gate voltage, so what you can do, you can create carriers here or deplete the carriers. So when you apply, for example, more than 0 gate voltage, you let's say deplete carriers. And when you apply a negative gate voltage, you create more carriers. So it depends on the p type or n type or electrons or holes. So what they have shown is that, so they made a Hall bar out of these structures, and they may measure the Hall resistance, and they sweep the magnetic field here. And what you see is this is the anomalous Hall effect coming from the magnetism of indium manganese arsenide. And when you have this negative gate voltage, 125 volts, so it's a huge gate voltage you see in the real device application, you need few volts, but here the oxide and other things actually uh, used in this device require high gate voltages. Okay, then what you can see when you apply a negative gate, you see the signal is very small. So it's not ferromagnetic. So these experiments actually prove that the magnetism in this material is carrier mediated and it's tunable. So you can tune the magnetism by gate voltage, which normally you cannot do much with the ferromagnetic metals. But nowadays also it's possible, because if you make a very thin ferromagnetic metal, few less than 1 nanometer, so you can also change the magnetic properties or tunability with gate voltage. But this you can do also with thick samples. Then the next question was, because the Curie temperature of this diluted magnetic systems was very low, below room temperature. So people were thinking how to integrate normal ferromagnets like iron, cobalt, or nickel with semiconductor channels, so that you can inject spins from the ferromagnet into the semiconductor, and the spin can move in the channel. You can detect with another ferromagnet. So for example, this is the source, this is the drain, and this is the channel material. And by applying a gate voltage, what you would like to do is change the orientation of spin. This principle of applying gate to change the spin orientation is called Rasva effect. Because Rasva initially proposed, it was long ago, that when your electrons are moving with velocity v and you have a material with high spin orbit coupling, and where the inversion symmetry is broken, so then when you apply electric field, this will give rise to a net magnetic field in the material. So the effective magnetic field electron experience will be cross product of the electric field you apply and the velocity of electrons. So with this effective magnetic field, spins will start to precess. So you should be able to manipulate the spin of electron by the gate voltage. So this electric field from the gate will change the orientation. So this is not same as, this is called a spin transistor, for example, but it's not same as the MOSFETs. So MOSFET, you either pull out electrons or so you change the carrier density, but here you don't want to change carrier density much, but very small voltage, which should be able to change the orientation of spins. Okay, so to do that, to realize this device, it was quite challenging after it was proposed in 1990s. So it was found out that everything is challenging here. How to inject spin from a ferromagnet into semiconductor, and how to transport them, and how to detect them, and how to manipulate. So these four things came out to be very challenging. So people worked for more than 20 years, and there was not much to see. But I'll show you what are the developments in this semiconductor spintronics. So it's not about only these spin transistors, but how also semiconductor can be used for spin orbit torque, or how it can be used for spin logic, or also spin qubits. Nowadays, it's getting interesting. But before going there, we need to understand what is the spin relaxation mechanism in semiconductors. No? Because you have to choose a semiconductor where you want to inject those spins. So electron spin polarization should stay there for some time. And you have to control with the electric field. Then you have to understand what is the interaction of spins with in the material. So there are many mechanisms. For example, first you create the spin polarization in your material by injecting from the ferromagnet or with some means. Then after some time or distance, the spin will be again coming to non-equilibrium state. So for example, they will be randomized. So this time is called spin relaxation time. And there are different mechanisms how the spins can relax. So one is it's after the names of the scientists. So Elliott effort, economical, and hyperfine interaction. So let's go to one by one, bit more in detail. So Elliott effort mechanism is just a momentum scattering by phonons or non-magnetic impurities. So if you have an impurity with a non-magnetic character, so magnetic impurity will be different because spin will be spontaneously dephased if you have a magnetic impurity. So that you have to reduce in your semiconductor. And nowadays semiconductors are very pure, so you can have very less magnetic impurities. So you have this is the momentum K prime, and this is the spin. So your electron is coming and getting scattered from this. And then what happens? The momentum is changed. Also spin is changed. So this is a probability. So we have to consider how probable is our electron getting scattered from an impurity in the material and or a nucleus and getting some another spin. So spin is getting flipped. So it's called spin mixing conductance or spin mixing state. So what you have to consider that so if you have a low spin orbit coupling material, that means you have lighter atoms, for example, silicon and carbon atoms. So they are lighter. So in those materials, so this mechanism will be very low. For example, silicon, you can expect spin orbit coupling due to momentum scattering will be very low. Another mechanism, which is called Econoff-Well mechanism. Again, it was proposed that when you have a material which lacks inversion symmetry. So for example, gallium arsenide. So it's not very symmetric material. So inversion symmetry is not there in the crystal structure. So when inversion symmetry is broken, so it's like a polar material. So you might have heard about different types of polar materials. So there is an internal electric field in those materials. So this internal electric field together with spin orbit coupling, so that creates a net magnetic field. So in this case, what can happen is that because when electrons are moving in such a crystal, so they have the spin orbit Hamiltonian here, which depends on the effective magnetic field. And that will differ from place to place when electrons move in the crystal because the inversion symmetry is broken and you have an electric field and electron feel this magnetic field. So that will dephase the spin polarization, and that is called Econoff-Well mechanism. And this is quite active in materials such as gallium arsenide. But in silicon has an inversion symmetry, also gallium arsenide has an inversion symmetry, also graphene has an inversion symmetry, mostly if it is flat. So this mechanism is very low. So it's dominant in gallium arsenide, indium arsenide, with such semiconductors. Then there is another mechanism called Beer-Arnault-Picus, so which is actually due to electron-hole exchange interaction. So in your material, there is always electron-hole recombination and creation operations going on. So you create electrons and the electrons get trapped and get the holes. In that case, and that is more active in the p-type semiconductor because you have more holes. And so in this case, you can consider this mechanism can also flip the spin. And lastly, there is a hyperfine interaction when electron spin interact with the nuclear spin. So if your atom have nuclear spin, then they will flip your spin polarization of the electrons. For example, silicon 28, carbon 12 have no nuclear spin, but if you have silicon 29 or carbon 13, so they have nuclear spins. So they can flip your electron spin polarization. For example, gallium arsenide also have nuclear spins. So this is not good for spin transport, but I'll show you results about that. So what is the main mechanism, as you see here, will be useful for spin control of spin polarization is this material where inversion symmetry is broken or if material have a high spin orbit coupling. So that material actually is very difficult to get spin transport because spin orbit coupling is very large. So difficult to also get spin transport up to room temperature. How is the spin orbit coupling? So spin orbit interaction. Let's see a bit more in detail. So you actually know this from your basic studies that how from the proton point of view or the electron point of view, we look at the spin orbit strength. So the spin orbit coupling, as we know, can give this effective magnetic field. And when you solve different, if somebody is doing some DFT calculation of some materials, so you might have seen that they calculate with spin orbit coupling, without spin orbit coupling. So maybe in some materials it's not very relevant, but in some materials it's very pronounced. And you have to add such a Hamiltonian with the spin operator with this effective magnetic field to your equation. So what can happen when you have a spin orbit coupling in your material? So for example, I take a silicon band. So it's a simplified parabolic band structure. This is the energy spectrum for free electrons. This is the energy and this is the momentum. So here up and down spins, so they are actually together. But if you have a material with a high spin orbit coupling, so for example, say semiconductors like indium arsenide, so what can happen is that due to high spin orbit coupling, these bands will split. So this is this green curve here you see, and the red curve, they split due to spin orbit coupling. And this green one is spin up and the red one is spin down. So this is theoretically fine, but can we see experimentally such behavior? Yes, of course you can see. So actually here we measured recently one semiconductor is bismuth tellurium iodide. It's called high Rasba spin orbit semiconductor. So as you see, spin orbit interactions should split the bands. So here is the angle resolved photoemission spectroscopy measurement showing how the bands are split. So you see not only two bands but multiple bands. So how to know the spin polarization, whether spin is up here, down here, how to know that? So you can do a circularly polarized dichroism experiment. So then you do right circular light experiment and left circular light and subtract from each other. Then you can get the spin sensitive data. And this red ones here is the, for example, spin up, and the blue one is the spin down. Okay, so if you measure, for example, silicon band structure, so it will look only parabolic, one band. But if you measure such a material, you will see these splitted bands. And this properties actually influence the material behavior. Okay, because of this huge spin orbit coupling, so what happened over years, it was very difficult to inject spin from the ferromagnet into the semiconductor and detect it also in the same by all electrical method. So it was very challenging to do that electrically. So, but what people have done earlier is, so you can find this review article if you want to know more. So if you have a semiconductor, if you shine a polarized light here, let's say it's here left polarized, so you can create spin polarization in the semiconductor. And in the semiconductors like gallium arsenide, they follow the selection rules. So you can, by left polarized light, you can create, let's say, down spin here. By right polarized light, you can find these off spins. And what people have done, use this scanning Kerr electron microscope. So they have a pump laser, like you pump, so you create the spin polarization. Then you also probe. This is the probe, and you then split with the polarizer here, beam splitter, and you can measure the K rotation. So rotation of It's called K rotation because when you have a magnetic moment in the sample or spin polarization, the signal will rotate, right, with some angle. Okay, so why I am showing that? Because spin injection detection was not possible by all electrical methods, but in optical methods, people could see what is the spin polarization they create in the semiconductor, and that helped us to find out to how to do it with electrical methods. So what I'll show you is some basic things. It will be helpful for students to find out how the spins are created in semiconductor and how they diffuse, dephase, and if you apply electric field, if you can drift them, and if you can apply a magnetic field, so that spin can also precess. So there are many experiments. I just take here a few examples from this paper. So here is a scale bar is 50 micrometer. It's a gallium arsenide semiconductor. It's a bulk material. So they shine this polarized light and you create spin polarization. The maximum spin polarization is, let's say, 55% here in the middle of the sample. And as you see the color code here, the spin polarization goes to 0 with a distance. Okay, so what can be happening here? So what you see here, spin actually diffusing. So you create spins, and in the semiconductor they diffuse because it's a non-equilibrium spin you created. So they diffuse in the material, and you see that how spins are diffusing. So in the equation, how to find it, that spin density with time, so with space and time. So you see that there's a diffusion term here. It's a diffusion constant, how spin density change with distance. And the dephasing is a lifetime of spins in this material. Okay. Now add another parameter. Let's say add an electric field. So you have a semiconductor, you apply this voltage, and you are doing the same experiment. So you create spins, and this is for 0 voltage. This is for 3 volt, 6 volt. This is 8 volt, and this is 10 volt. So what you see here is that you create spin polarization, and with electric field, you actually drift this spin polarization. So the spin is getting drifted with the electric field. So it's actually working in the similar way as you solve the charge transport in semiconductors and metal. Metal drift will be very less because you have lots of, and there is not much electric field. But in semiconductor, drift is a dominant factor. So what equation in the equation you add this drift term. So this is a drift velocity. So then equation looks like this. So we are trying to develop a equation for the spin transport in semiconductors. Then what you can do, so because you know spins are also sensitive to magnetic field, so you apply a magnetic field and it's perpendicular, so spins will precess with Larmor frequency. And what can happen is that what you see that with increasing the field, you see the spin density also going down. And so because we don't apply electric field, so I remove the drift term here. So only spin precision is added here. So spin precision means this is spin density with Larmor frequency here. So Larmor frequency depends on the applied magnetic field, mu bar and G factor of the material. So this is a complete equation for the spin diffusion, drift, precision, and dephasing. So you have a electric field applied, magnetic field applied here. So then how the equation spin diffusion, drift, precision, dephasing equation look like. So this is very simple, and you can see this all in experiment. So that was the beauty of this optical experiment when electrical detection was not possible. Then moving forward, they tried to make some practical devices. So the practical devices is that they put these ferromagnets to inject, but the detection was not possible with the ferromagnet, but they could measure how spin injected from the ferromagnet. So the previous experiment, it was all optical. You create spin polarization in semiconductor by optical means, also detect by optical means. But here, what you are doing is by electrical spin injection from the ferromagnet into the gallium arsenide. So you apply a bias, so electrons from iron are getting injected into the semiconductor, and they are also diffusing here. So this is the real device picture, and here is the similar optical image they create. This is a Kerr microscope. And this is the iron, and so below that they could not see, but in the side, what you see, the spin density, how this is diffusing in the channel. So this is with this length scale. Okay, then how to know if it is spin? So you can always apply a magnetic field, so that spin will precess. So you see such a line shape. It's called a Hanle spin precession, as I showed you in the metallic case. So this makes sure that you are measuring spins. So this was also possible. Also, I have shown you in the metal case, there is a spin Hall effect. No, actually, spin Hall effect was first realized in semiconductors like gallium arsenide in this paper. So they took a metal, they took a here a semiconductor gallium arsenide and applied a current here. So they could see what they could see is this optical Kerr microscope that one type of spin, this red one, is accumulated in left side, and the other spin accumulated on the right side. So this is the real device picture as you see with the microscope. Okay, and this is the Hanle measurement. How this spin density you create depends on the magnetic field. So once you apply magnetic field, so spins will dephase. Okay, then people went forward a bit more and they prepared a spin light emitting diode. So what is spin light emitting diode? So you know what is light emitting diode? So it's like a semiconductor heterostructure. It's a N-type semiconductor. It's a P-type semiconductor, and in between you have an intrinsic semiconductor. So they can have different band gaps, so that you can make such a heterostructure, so that you have create a quantum well. So what you do in the light emitting diode, you create inject electrons from this side and electrons and holes from the other side. They recombine, create light. But if you use a spin, you want to make a spin LED. So what we can do, inject spin polarized electrons from the ferromagnet. And this semiconductor should be such thickness that spin can survive and come to this quantum well. And they recombine here, and the light coming out from this LED will be polarized, circularly polarized emission. Okay, and people have detected this with electroluminescence intensity. This is the polarization of the light coming out, and this was done around 2000 in these two papers. And also, it was interesting to see that people also could inject spins from a ferromagnetic STM tip, scanning tunneling microscope tip, but it's a ferromagnet, and this is a gallium arsenide. So they could inject the spin into gallium arsenide. And here is a cartoon just showing how spins are injected, and it can be flipped when you have a step like feature here. But the real papers are here. So how they could do that? So this is a gallium arsenide, and this is a STM tip with a nickel tip. They prepare in ultra high vacuum. So it's a ferromagnet tip at the end. So you can apply some bias to inject spins here, and then you see at the light emission. So the polarized light coming out, you can detect the polarization what you see. So this is the with the K means the energy of the injected electrons, and here you see the polarization. So all these experiments so that you can inject spins in the semiconductor and detect by optical methods. So with this, if there is any questions we can take, and then I will move to all electrical methods.
Okay. We don't
There is
have
nothing
any
in the chat room,
in the
so
chat.
maybe
If
maybe
anybody
we
wants to
proceed,
ask,
and I think people have time to think about and
yeah,
write.
yeah, I think at the end we can take the
Yeah.
questions then. Yeah.
Okay, so you can keep on writing your questions. So we can answer that at the end of this part. So this was all this experiment. What I showed is so it actually helps us to understand the systems, and it gives lots of information to make real devices. And in 2007, it was first people have reported all electrical creation and detection of spin transport in gallium arsenide, but all at low temperature, because the spin don't survive up to high temperature in gallium arsenide because of high spin orbit coupling. So what people have done, so like a similar device I showed you for the metallic spintronic case. So they have an injector here and a detector. It's a gallium arsenide. Injector detector are ferromagnets like iron here. And depending on the magnetization of the injector and detector, so what you see is the spin valve signals, and this is hysteretic. And in the middle of this signal, you see a peak-like structure. So this is a magnified version of this signal here. So this peak-like structure, I don't go into the details, and it is coming from the actually nuclear spin interaction. So you create this spin polarization in the gallium arsenide, and your spins are actually staying bit polarized bit for longer time because of the nuclear spins. It's called dynamical nuclear polarization. So your electrons around this nuclear spin can stay a bit longer. Okay, and as I have shown you for the metallic spintronic devices, so if you apply a magnetic field perpendicular to this, so you create spin precession. So you see this Hanley effects for the parallel case, the black one, and for anti-parallel case of the ferromagnet, it's the red one. And this is the temperature dependence of the signal. As you see, when you warm up, your line width of the Hanley curves is broadening. So the line width is broadening. That means, so the narrower the line width, higher the spin lifetime. So from this, you can find spin lifetimes of nanoseconds in this gallium arsenide. So far, so good. So there are lots of studies with the semiconductors, and gallium arsenide among these compound semiconductors was very good for spin transport, but most of the studies were limited to low temperature. But to make some practical devices, we need to go for room temperature applications. And for that, actually, it was required to go for low spin orbit material. Of course, there will be challenges to find, again, mechanisms for control of spin polarization. But if we first realize how spin can be created in silicon, and that will be again helpful, then we can think again about how to manipulate them. So silicon is interesting because it's the mostly used semiconductor device, and the industry is very mature in this case for making logic devices. And it have low spin orbit coupling, and nuclear interaction is very less. Because 96% of the silicon is zero nuclear spin. And nowadays you can find silicon even and there is no isotopes. So you can get very pure silicon. So what we find in the beginning, it was very challenging also to inject spin into silicon because in the previous case with gallium arsenide, they could epitaxially grow this gallium arsenide, and they can use the Schottky barrier between the ferromagnet and gallium arsenide to inject spin because Schottky barrier acts as also as a tunnel barrier. But in case of silicon, if you put a ferromagnet on silicon, so the interface will have some silicides that will actually dephase all the spins. So therefore, it's very important to get a tunnel barrier in between. So that is the material point of view, from the material point of view. Also, it will act as a spin polarized tunnel barrier because tunnel barriers we know are good for spin polarized tunneling. So once you have this ferromagnet, you tunnel to this barrier and create spin polarization in silicon, and you create the spin splitting in silicon. And this spin polarization goes like this. So you have ferromagnet, you have this barrier. It can be aluminum oxide, magnesium oxide. So you have this Schottky barrier, but you have to use highly doped silicon to keep it narrow, so electron can go through. Then you create the spin splitting in silicon. So how to detect it? So you can again use the Hanle spin precision measurement. So you apply a perpendicular magnetic field. So your spin splitting delta mu you create in the silicon by spin injection should be go to 0 state. So they will be equal at this stage. So your voltage signal should behave in a similar way. And you can also solve this equation, but you have to rule out, means you can remove the drift or drift term, because if you don't apply the electric field, so that should not be present. So you can also solve the equation of the conductance, how the spin conductance, up spin, down spin conductance, and how the spin accumulation behaves in the semiconductor. And the voltage signal you see here, that is directly proportional to spin accumulation you created. Okay. And when you apply this magnetic field, so spin should precess, and you should get no spin polarization at some point. So if you do a time resolved experiment, you should be able to see this, but we don't do time resolved experiment because optical experiment is challenging here in silicon because it's an indirect band gap. But when you do this electrical measurement, we see such a Hanle effect. And from the line width of this signal, we can find the spin lifetime. And this is all at room temperature. So it's around 150 picosecond. And also what we can do, so that previous measurement was with the bulk silicon. Also, you can make some quantum wells of silicon. So you can actually use some ferromagnet, then a tunnel barrier. Then you can create a silicon quantum well by using some low work function material at the other side. So their band, instead of bending up, it goes down, and you create these quantum well states. And what we did here, we actually applied a perpendicular magnetic field to create a spin split band in the silicon 2-deg. Okay, so you have a ferromagnet here, and you have a spin split 2-deg band, and you can do tunneling experiment in this. And when you hit these bands here, then you should see a maximum of the tunnel polarization. And that's what we see here. And when you go to, we tune the electric field to go to these states, we see this maximum in the magnetoresistance. Okay, so far so good. So we could inject spins and detect spins in the semiconductor. But what about the lifetime? How this is compared to electron spin resonance experiments in semiconductors? So actually, it's orders of magnitude less what we see. So in our measurement, our lifetimes are around less than nanosecond. But in ESR, electron spin resonance experiments, actually it's somewhere in few nanoseconds or up to 10 nanoseconds. So, but ESR experiments are done in a bulk sample, but we are dealing with a device here, and we have the interfaces with ferromagnets. For example, we have a semiconductor, we have a tunnel barrier. So it's a very ideal case here, but it have lots of pinholes and interface roughness. So that actually interface roughness can actually create stray magnetic fields on these semiconductors. So the stray magnetic field is also very inhomogeneous at different points here, and that can also reduce the spin lifetime. So you can find this in this review article. And in silicon, also you can do spin transport. So in this paper, it has been shown that if you have a ferromagnet injector and a detector here, so you can have a channel length, you can inject spins from here and detect it here, and you can get very large spin signal. And this is the spin valve signal when you have parallel anti-parallel magnetization. And it's the Hanle spin precision signal for parallel and anti-parallel case. Okay. And the tunnel spin polarization achieved is because it's an MgO barrier used here up to 90%. Okay, so I'll not go in details anymore. So we have bit up with time. So also silicon is an interesting material because it have low spin orbit coupling. So for quantum spin, and it's called spin qubits. So you can make a quantum dot here by applying some gate voltages. So you define your quantum dot, and you can deal with single spins. So it's a single electron transistor type of device. And you can also uh, create and detect these spins and their states by this microwave line. So which actually now scaled up. So this is, for example, in I think last month, it's a news from IMEC. So they created the silicon spin qubit up to 300 millimeter wafers. So you can find lots of spin qubits. So there's a real development happening in silicon spin qubit systems. But the spin qubit have to work with low temperature. But the methods developed for creating the spins and uh, measuring the lifetime. So these things are helpful for development of this technology. And so what is the other perspectives for semiconductor spintronics? For example, I have shown you how this Raspberry spin orbit coupling can be useful. So then with this Raspberry materials, so you have the spin orbit coupling. So if you add a magnetic exchange, so you can create new states of matter. So you create a magnetic exchange gap in this semiconductor. And if you add a superconductor proximity, you also create the topological superconductors. So these are quite useful for studies in uh, quantum physics. And also the spin orbit physics in semiconductors can be interesting for many things. So not only for spin Hall effect to spin transistors or spin orbit torque, but later on we'll see how semiconductors become topological insulators. So these are lots of interesting things. And to summarize my talk for this part, so what I have shown you that, so one can optically create spin polarization in semiconductor and detect it also by optical method. Also spin Hall effect was also first observed in gallium arsenide semiconductors. So later on now they are more used in the metallic systems for making more active spintronic devices. And magnetic semiconductors, they are tunable, but they are having low Curie temperature. So spin qubits are also interesting. And we can see how we can do all electrical spin injection, detection, transport up to room temperature in semiconductors. So with this talk, I finish, and in the next talk, I'll show you on 22nd February. So graphene and 2D heterostructure spintronics and topological materials for spintronics. And so this slide I already showed. So more things comes how the spin behavior in topological quantum materials can be interesting. And this is about how we can make a graphene spin circuit, and with proximity effect at will, at some point, we can create spin orbit and magnetic exchange interaction. And in the topological quantum materials, I'll show how these topological properties and their spin textures can be interesting for spintronics. Okay, so with this, I stop. So if you have any questions.
Thank you, Saroj, for this excellent talk. I mean, it's really exciting, and I think you have built the groundwork for some real exciting summary of on topological insulators in the next class. So, any questions? Okay, we have one question.
One question from MK Huda. can you make a comment on the spin transport equation, how it will be modified for Dirac materials? So yeah, so again, it's a question. So what I showed you today, actually, this is more, I think, the basic things for next lecture. And so Dirac material, for example, you mean maybe graphene, no? So I'll actually, there will be 1 hour talk about graphene. So we'll see there. So there will be new properties coming into picture. But you are not always at the Dirac point. So you can go to away from the Dirac point. So the same equation is valid. Very close to the Dirac point, to do a spin transport measurement is very challenging, and because there will be some pseudo spin coming into picture, but that I will discuss in next week's lecture. So it will not be modified, but you will add some few extra terms into the picture. Okay, another question.
Another question, yes.
Silicon is used in spin transport just because it's small spin orbit coupling, but it is an indirect band gap semiconductor. So it has more non-radiative loss in gallium arsenide source. Okay, so yeah, so it's a good question. So silicon is an indirect band gap semiconductor. So we cannot do optical experiments there. So we tried optical experiments. So the signal we see is very low. And so what I showed you today with silicon is all electrical measurements. So electrical spin transport, it's not a problem in indirect band gap semiconductor. So gallium arsenide have the advantage. So therefore you see lots of results with optics with gallium arsenide because they follow the well defined selection rules. And so for optical experiments, for example, making spin light emitting diodes, so spin LED or spin lasers, so gallium arsenide is preferable. For electronic spin devices, so silicon will be good. But there is no practical device yet, so there are many competitions. So we don't know whether this will be really useful in any applications, but the knowledge and information we get will be somehow useful for building something else. So for example, the silicon spin qubit, so they can use the information from spin transport equations we use. So that is my point.
Any more questions?
Looks like I think there are no more questions, but Saroj, we would like to thank you for a wonderful talk. And it was really lucid as we expected. And we hope to see you again next time. And I'm sure with your topics for the next time, I'm sure people are looking forward to it. And I will also take this opportunity to thank for you. I'm telling you, Sir Professor Dash, that there is a team of students, Ali Child, Anupam Bhattacharya, Vishal Bharadwaj, of course, with the help of Niladri Banerjee, they organized this. So we all thank them also. And we hope to see you next on Monday and for a even better. So it was quite interactive, and I think it's a good idea to have in between question hour session. I was just wondering how it will play, but it looks it's a good idea. So very nice. Thank you. Thank you.
Yeah.
And yeah. So all
thank you, madam. So I tried to keep it a bit simple. And so what you saw in today's lecture, that actually helped us to understand the 2D materials, also topological materials, because there is a continuing research field and people are moving from, for example, I was more doing semiconductors before. So when new materials comes in, we can use our technology and knowledge to understand those things, some timely subjects.
Yeah, so you explained it from the very basic and very beautifully you progressed. That's very nice. Thank you. Thanks a lot. So Niladri, you want to say something?
So we are, I'll stop the recording now and we'll try to upload, hopefully, fingers crossed, everything goes smoothly. We'll try to upload that in YouTube. And we already have all the email IDs and we'll send the link. I mean, that will be available. And we meet same time, 10 a.m. GMT on Monday for the second part of the talk. Yeah,
Okay.
yeah, that's it. So,
And
okay,
bye.
thanks everybody. Thank you.
Bye.
Bye.
Thank you. Bye-bye.